Hello everyone. On today's video, we are going to perform a drop test analysis. We are going to include only one single part and we are going to do an explicit dynamic analysis in, of course, in Abaqus graphic user interface. So let's start. We have already prepared a model and we import it via part module, the specimen. Okay, perfect. So now let's go and create our material for a dynamic, let's say that's aluminum. For a dynamic analysis, we are going to include elastic properties, Young modulus in units of megapascals and Poisson ratio and 0.3. And for dynamic analysis, we also need the density of the material in consistency with millimeters, -9. Okay, perfect. We create the relevant section. Aluminum, solid. Okay, perfect. And with this button, we assign it on the part, on the specimen. This green color means that the part has an assigned section. So next, we have to create the impact surface, the ground floor, let's say. So this is analytical rigid. It's very common to use an analytic rigid surface for the ground, and let's draw it. Just draw a line, and let's say that this is 200 millimeters, and let's quit sketch. This is the ground floor. We will also need a reference point on this surface because it will help us assign the boundary condition. So this is the reference point, the yellow on the middle of the surface. Okay, now let's create the instance including both parts, auto offset, and now we have to translate our part. In drop test analysis, what we usually do is to bring the specimen very close to the impact surface and then assign the relevant velocity as a predefined field. We have to calculate the impact velocity the moment exactly before the impact. From the free fall formula, if let's say we want to make a drop test simulation for an object from 2 meters, we have to use the free fall formula and calculate the velocity exactly before the impact. It is very easy. So what we have to do here is to translate the specimen close to the surface. I use this technique. Click OK first in the middle. Again, I will move it upward. Always you have to read the Abaqus and notes here, and I will bring it up, let's say 20 millimeters in the y-axis up. Okay, now I will rotate it a little bit to give an inclination on the part. Start point for the rotation vector, the end point for the rotation vector, and let's say rotate it 30 degrees. It's okay for now. We can go on. Okay. We didn't mesh the part. As we said, we have to mesh only the specimen and not the ground. So it's a yellow color perfectly. Let's use explicit from the element library here. I do not use reduce integration, hex elements linear, perfect. So next, the average global size is 5, let's make it 2. Okay, let's make it 1.5. Okay, I think it's okay. Let's mesh it. Nice, it looks good. Okay. So next we have to create a time step for the analysis. It's an explicit dynamic analysis. And here we have to define the time period. I believe that for the impact we will need 10 milliseconds. I think it's okay. We'll see. Mass scaling, okay. Let it as it is now, and we will see if we have a very small time step. So the field and the history output have been created automatically, but let's ask for values every 0.1 millisecond to capture the weld event, and the same as here. Okay, perfect. Interactions, yes, we have to include interaction for the two parts, of course. Tangential, I usually use penalty method. Let's make a value and hard for the normal. And here we have to create a general contact. Instance Gaussian analytical rigid part. Okay, yes, we forgot to create a surface for the analytical rigid. Surface 1. Click the analytical rigid surface and brown or purple, brown color for the contact. I think that now we will be able to create the interaction, general contact. Yes, perfect. Just here we select the interaction property 1 we created previously. Okay, let's move with the boundary conditions. Symmetry and symmetry, just click the reference point, and all the degrees of freedoms will be constrained by clicking this, the last one, for the whole analytical rigid surface. Again. So here, the predefined field. As we said before, we will assign velocity in the initial step, and let's click this set, the specimen, and I had calculated that if we leave an object fall from 1.5 meters height, the velocity before the impact is being calculated approximately 5 meters per second, 5.5, something like that. So here in the V2 cell, this is for the y-axis. We have to put the value, since we work in millimeters, minus 5,000 millimeters per second. So you can see the arrows here. So I believe now we are ready to create a job. Let's create, cancelled, let's name the job drop test 1.5. Drop test 1.5. Use these processors, create the job, submit job. Okay guys, as you can see here in this table, if you right click and monitor the job, our analysis is running. This is the increment, here's the total time, since we have only one step time, and the total time is the same, and this is the stable time increment for an explicit analysis. It's very crucial. It's quite big now, it's okay. Here we can see the kinetic energy and the total energy. As you can see in the beginning, the kinetic energy and the total energy is the same and constant. The total energy must be constant or almost constant with a very small deviation. Here in this time step, on this point, you can notice a drop of the kinetic energy, that means that the impact has occurred. So we can leave the analysis running, and we can see some results by right-clicking and click results, and here we can see the drop. You can see the drop and the rebound. You can see there. Okay, you can go back. The analysis has reached the almost the 4 millisecond, but the impact has already occurred. I used to close the ADB and reopen it if you want to see the evolution of the rebound. Okay guys, thank you for watching. This is from me today. See you next videos. Bye bye.